Now we've looked at what happens as we remove energy from a system through damping. So it's applying a non-conservative force to remove some of the energy. But we can't just remove energy, we can also add energy. So let's imagine now that we add energy with a special type of force, a periodic force, which is described by the equation F times sine omega t. So this is a sinusoidal force. In that case, we can get what's known as resonance. So let's have a quick look at some of the mathematics and then we'll discuss where you'd see this. So if we're applying this force, we've got the total force acting on the system is equal to F0 sine omega t, that's our periodic driving force, minus B dx dt, that's the damping force that we were modelling as proportional to V, minus kx, this is for a spring, so we've got the spring force there, and that is the net force, so that's equal to m d squared x dt squared. Now, this is quite complicated to solve. If we do solve it, we end up with the solution of the form x is equal to a cos omega t plus phi, where a is the amplitude, and it's really complicated. It is equal to f naught on m, all divided by the square root of omega squared minus omega naught squared all squared plus b omega on m squared. Okay, so let's just discuss what's inside that A thing. We've got the omega, which is the frequency of the force that we're applying, the periodic driving force. Omega naught is the natural frequency of the system. So for the spring, which we're describing here, it's the square root of k on m. But pendulums and other objects have their own natural frequencies that they want to vibrate at. And B, remember, is just the size of the damping. So if B is really big, there's lots of damping. Now looking at that A, it's possible to make it into a really big number. If we make the driving frequency, omega, very close to the natural frequency, omega naught, then on the bottom we've got omega squared minus omega naught squared, which is approximately equal to 0, sorry. So if we, in that case, had a small damping, so the B term was really small, then we're dividing by a really small number, and when we divide by a really small number, we end up with a large number. So in the case where omega squared was exactly omega naught squared and we had 0 damping, we'd actually end up dividing by 0 and having an infinite amplitude. Okay, so obviously in practice this couldn't really happen. We would have to have some damping, but we can end up with really large numbers here. So when we have a really large number for that amplitude, this is known as resonance, and it causes our oscillations to have a much larger magnitude than they otherwise would do. So where you've probably used this in everyday life is if you imagine pushing a child on a swing. You don't apply a constant force, you apply the force periodically, and you want to time your pushes with the swings of the child. So you don't push the child at random points along the swing, you push the child at the end of the swing, and then once they come back to you, you push them again. And this actually causes resonance. So that's what causes the oscillations that the child is undergoing on that swing to increase in magnitude. Okay, so now you've heard a little bit about resonance. Now I want you to look at a system and make a bit of a prediction about what you think is going to happen. Okay, what I have here is a series of pendulums. They're all connected along this bar at the top. In a minute, I'm going to drive these pendulums by swinging the large silver ball at the other end. Now, before I do that, I want you to use what you've learnt about resonance to predict what's going to happen to these different coloured balls when I do that. Be as specific as you can in your prediction.